have an equation that, or whenever you have a proportionality where something is directly proportional to another, there's always a proportionality factor. There's always a number you have to put in there on one side of this equation or the other to make it an equal sign. So it's not a proportionality anymore. And the thing that Newton discovered is that it's mass that's a proportionality factor if you put it on this side of the equation. So force equals mass times acceleration. If you put the mass on the other side of the equation, then it's 1 over the mass, and that becomes the same equation in the end. And so what he really discovered is that the acceleration for any given force, the acceleration is always inversely proportional to mass. More mass, less acceleration. Less mass, more acceleration. Okay? So here you have a basketball player passing a basketball with a large acceleration. With the same push, gets a small acceleration pushing the SUV. Right? Even though the forces are the same, the accelerations are different. And we're going to see that again here in a second. So Newton's second law of motion says that force equals mass times acceleration. This is how it's usually written. It's also acceleration equals force over mass, but it is a vector equation, so you have to include the vectors in it. And it is the net force that we're looking at, the total force. So if you're driving your car around the street again, and you're just barely pushing on the gas just to barely keep your car going the same speed the whole time in the same direction the whole time, you're not accelerating because your velocity is remaining constant. So why do you have to keep your foot on the gas? Because putting the foot on the gas just a little bit applies a little force to the car. Why do you have to do that? Because there's friction pushing backwards on your car all the time, right? Friction pushing against your wheels, there's friction inside the wheel bearings, there's friction all over the place, air friction, whatever. Little mosquitoes hitting your window, thank goodness for killing mosquitoes. As all that adds up, then you have to add just a little bit of forward force to keep going, right? So the net force is equal to mass times acceleration. And you can split it up. If you just have one dimension, this equation becomes simple. It's the force in that direction, that x dimension, equals the mass times the acceleration in that dimension. But if it's two-dimensional force, two-dimensional acceleration, you have to split it up into the x-directional forces and the y-directional forces, the x-directional accelerations, the y-directional accelerations. But once you have that split up, then you can also use kinematics. Because once you have acceleration, you can start dealing with velocities and displacements and things like that, right? So it's inexorably tied to kinematics once you have the acceleration. Here's an example of a very simple problem with force. You have this net force going forward. Why would this be the net force? What other forces might be involved in here that contribute to this net force being forward? First of all, the person pushing the lawnmower is actually going to be pushing along the handle. The force that he's pushing with is actually downward. And what other forces are involved in here that might contribute to this downward force that he's using ending up forward instead of downward? Have any of you mowed a lawn before? What happens to the lawn as you push the lawnmower? If you push the lawnmower harder, what happens to the length of the lawn after you've cut it? Does it become shorter, or, does pushing the lawnmower affect the length of the cut? It should. If you push really hard on the lawnmower, it will actually press the lawnmower down into the grass a little bit. If you don't push very hard, if you just kind of like push with two thumbs, it's actually going to rise up. It'll actually, the lawnmower will actually kick up and kind of ride on top of the grass. And you'll get humps in the grass every once in a while. Most people aren't really aware of this unless they've watched children mow lawns, because children have a tendency to pick the easiest path and push in the easiest way, and have a tendency to have a wavy lawn on your lawn. So you have to teach them to push with a constant push, because that gives you a constant push down, and the lawnmower is a constant height. But as you're pushing the lawnmower down, the ground is actually pushing back up on it. And so there's an upward push on the lawnmower. So a downward force that you're pushing with and an upward force can result in a straight force this way. Right? There's also some other forces, if you get really technical, that are internal to the lawnmower, but we won't get with that. But if your net force is here, that's all we need to know, because Newton's law only wants to know the net force. There's also friction. Probably somebody said that, and I didn't think it. But anyway, the net force is all we care about. So they've given us the net force, so we're good to go. And they've told us that it's 51 newtons. They've told us the mass of the lawnmower. Plug it into the equation, you get an acceleration, you're done. It's really simple. Because it's in one dimension. We're only dealing with net force in this direction, and our acceleration is also going to be in this direction. And that's something that we should realize, that because it's a vector equation, the net force and the net acceleration, the net force and the acceleration will always be in the same direction. So if you want to know which direction the net force is, look at which direction the acceleration is. If a airplane is accelerating off to the northeast or something like that, then you know the net force is to the northeast. You don't know how much it is, maybe, unless you know the mass of the plane and the acceleration. But you definitely know the direction because it's always in the same direction as the acceleration. Here's an example where we have two forces acting. We have drag force, and here they're showing friction force forward. Why would they show friction force forward? How does a car accelerate? By turning its wheels, right? And its wheels grip the ground with what? Friction, right? So the grip of the wheels on the ground is friction. So that frictional force is actually the force that propels the car forward. It's also friction force that slows it down as the wheels slow down, or as they lock up and skid, or whatever it is, right? So friction is quite a versatile force. And then you have drag force. This drag force is usually considered what we call air drag. So drag is usually due to a fluid. So the drag force is from the air friction backwards, so you can think of it as. And here we have the drag force and the frictional force being constant, or being equal and opposite. So when we add them together, we have a velocity of 10 meters per second that is just constant, right? If you add this one to this one in vector form, they cancel each other out to 0. However, in this picture, we have an acceleration forward of 10 meters per second, which means that our friction force forward is actually greater than our drag force backwards. Now, they may not have drawn it that way, really, but we know that it has to be that way because we have an acceleration forward. So we know our total force has to be pointing forward. And if we know the acceleration is 10 meters per second, and we know the mass, which they didn't tell us, let's say that we do know the mass. Let's say the mass is 1,000 kilograms or something like this. So we know the mass as well. Then we can calculate the force. If you have the force and the or the mass and the acceleration, then you can take the acceleration times the mass and get the force, right? Mass times acceleration. So it would be 10,000 newtons because force is measured in newtons, named after Isaac Newton. Force is kilogram meters per second squared. Here's another one where we add several forces together in one dimension. We do have two-dimensional force here, problem here, where the weight downward of this rocket sled is countered by a force that they give this capital N to because they call it the normal force. Anytime you press two objects together, an object on the ground or an object on a slope, like skis on a ski slope or a book on a table or something like this, anytime two objects are pressed together by surfaces, there's the pressing force that holds the one object to the surface, and then the surface reacts with a normal force, which is 90 degrees to the surface connection, or 90 degrees to the contact. The reason they call it a normal force is because normal means 90 degrees. So this is the normal force, this is the weight down, and they're equal to each other in this case. They're not always equal to each other, but in this case, the weight down and the normal force up is equal to each other, are equal to each other, and they cancel out. So all of our forces that are going to add up and to make a total force are in the x dimension or the horizontal dimension, so it's just one dimensional again. And we can actually just use this form of the equation since it's all in one dimension, just make sure we get our signs correct. So in this particular problem, we have 4 thrust forces that are pushing the sled forward. And they just stack them all up here to show that it's a very, very long vector after you add them all together. And then we have 1 frictional force backward. Okay? So the net force is going to be 4 thrusts, thrust plus thrust plus thrust plus thrust, 4 times thrust, and then minus friction because the friction is in the opposite direction, so it's minus friction. And that is equal to the net force. And the net force is always equal to mass times acceleration, so this thing is equal to the mass times acceleration. And they want to solve for the thrust. So we solve for big T, and it turns out that 4 times big T is going to be equal mass times acceleration plus the friction. We plug in our numbers, solve for T, and we get the thrust at 2.5 times 10 to the 4 newtons. Newtons, kilograms, meters per second squared. So it's really not that different than dealing with acceleration and velocity and everything else with vectors, but it is a different thing. It is the thing that causes the acceleration force. Right? And I think that's enough to be getting on with. There are many other examples. Here they do one in actually 2 dimensions, where they have the net force equals the mass times acceleration, where the force is an I hat j hat thing. And this is not necessarily a two-dimensional problem, because what they want to know is the magnitude and direction of the force, not necessarily, they don't want you to work it out in 2 dimensions yet. So if you do this, use the Pythagorean theorem to find the magnitude of it, and then you use the inverse tangent to find the direction of it, and you can do that pretty easily. The rest of it they just do in, well, actually this one they do in 2 dimensions. So let's look at one in 2 dimensions. So we have this particle and all these forces acting on it. We have one force in the negative x direction, one force in the positive y, one force in the negative y, and one force in often at this angle. When you're dealing with forces like this and you need to add them together to get the total overall net force, you need to break up any force that is not directly in the direction of a coordinate into its components. So the F1 has to be broken into an F1 in the x direction and an F1 in the y direction, and then you split off the forces in their 2 dimensions. So here we add up all the x dimension forces. We have F1 and F3x. So we have part of F1 is in the x direction, and all of F3 is in the x direction. So they have F1 of x, which is the F1 cosine 30. And notice that they just kind of gave it its positive direction, because we know that it's pointing in the positive x direction. So it's just F1 cosine 30 with a positive in front. And then the negative F3x is just negative F3, right? It's just the negative 5 newtons pointing off in that direction. And that has to equal the mass times the acceleration of this particle in the x direction. So it's only equal to part of the acceleration, not all of it, just a part of it. Just the acceleration in the x direction. And then the same thing in the y direction, except in the y direction they have 3. They have this one, F4, they have this one, which is a negative force, so that one's going to have a negative in front of it. And then they have a piece of this one, the y component of F1 will also be in there. So the y component of F1 is pointing up, so it's positive. F4 is pointing to the right, so it's positive. I mean, to the up and not to the right. It's pointing up, so it's positive, and this is pointing down, so it's negative. And those have to add together to equal the mass times the acceleration in the y direction. Solve them separately for the accelerations, and you have 2 components for the acceleration that you're going to build a vector out of. Now you may notice that I'm moving faster today, and I've been doing that for a little while now, a little bit of the time, but today I'm definitely moving faster. And there are 2 reasons for this. First of all, you've learned enough already that I'm hoping that we can move a little bit faster through things. And 2 is I want you to learn to kind of think faster. If I'm moving too fast, though, don't be afraid to say, hey, can you repeat that, or can you slow down and give us a better explanation of that? This is a good way to help you learn, is to learn to do things faster. It's just a natural way of learning things. So it helps to train your brain. But if it's too much, don't be afraid, because probably you're not the only one. I have a hard time gauging that. I kind of look at people's reactions to things to try to see how they're doing this. If I get bewildered looks or looks of panic, or people sweating blood from their eyeballs, then I'll slow down. But otherwise, I have to go on what you tell me. Are there any questions so far? We've burned through the first couple of sections here pretty quickly. First 3 sections pretty quickly. Any questions about how forces behave? Okay. We're actually going to introduce you now to something completely new that you've heard of before, almost certainly, but maybe you don't Maybe you've never done any science with it, and that is momentum. Because in truth, when Newton was doing his work, he actually didn't. It actually wasn't force equals mass times acceleration that he figured out. It was actually force equals the change in momentum of a particle, and that was something. It's a subtle difference, but it is quite important. So Newton's second law is actually more correctly stated as net force equals dp dt, or the time derivative of the momentum vector. Well, what is momentum? You've heard of momentum before, I'm sure. Well, what is it actually? Momentum is the mass times the velocity of a particle. So if you take the time derivative of the mass times the velocity, like here, then you will actually get the mass times acceleration. So force equals mass times acceleration is a simplified version of Newton's second law. And the force equals time derivative of momentum is actually the complete version of it. But this actually gives us an introduction to something, another very important thing in physics, maybe one of the most important things. If you went through physics and gathered up, the 5 or 10 most important things in physics, momentum would definitely be on the list. And why is that? Because momentum is one of the few things in the universe that is truly conserved. Now, this is what we call linear momentum, the momentum of a particle moving in a straight line. Linear momentum is technically only a version of a different kind of momentum we call angular momentum. So we don't usually say that linear momentum is the end-all of the universe. We usually say that angular momentum is. And we'll learn more about angular momentum later. But momentum is something that is conserved. What does that mean? Anybody ever heard the term conserved in a scientific sense before? Conservation of something? Yeah. So it's usually this idea that if something is conserved in the universe, then it has always existed there. It always will exist there. You cannot create it. You cannot destroy it. Right? You can't. It's just there. The only thing you can really do with it, if it is conserved, is move it from one place to another. Transfer it back and forth from one place to another. So momentum is one of these things. Can anybody think of another thing that's conserved in the universe? Energy, matter, anything else? It turns out, what's that? Okay, heat is a form of energy, technically, so heat kind of falls under the energy thing. And technically, it turns out that neither of those things is conserved. We used to think they were, right? But this is one of the big, holy grails of science, is to find something that is truly conserved and then try to prove that it's conserved by trying to unconserve it, right? And it was Einstein, again, we'll mention Einstein every other day in this class, but it was Einstein that actually discovered, theoretically, that energy is not conserved, and neither is mass or matter, right? And it's actually his very famous equation. What is this famous equation? E equals mc squared has E for energy and m for matter. And he didn't just make this equation up. He was actually doing some very complex calculations. When I mean complex, it was doing algebra in many dimensions. Algebra in many dimensions is one of the most painful forms of math there is. And it included also some calculus as well, quite a bit of calculus. And he came to this equation where it was a conservation of energy equation that he recognized, because everybody recognizes the conservation of energy equation. But he had changed some things when he started the conservation of energy equation because of something else that somebody else had discovered. Before him, a guy named Maxwell discovered that the speed of light was a constant. And so Einstein said, well, if the speed of light is a constant, in other words, speed of light was one of these things that was kind of conserved. It was a constant throughout the universe in a vacuum. And so Einstein said, if the speed of light is conserved, how does that change Newton's laws? How does that change all the work that Newton did and everything that's been done since Newton? And so he essentially went through and worked out all the stuff that had been done since Newton using this idea that the velocity of light doesn't change, and including that in the calculations, because there are different places where that fits in, especially when you're doing electrodynamics like he was doing. And what he discovered was that the conservation of energy equation had everything that it normally had. It had kinetic energy, and it had potential energy, and it had all these other energies in it. But there was this thing in it too, mc squared. And he's like, what the heck is that? And because the c is the speed of light, which is a constant, and mass is just matter. Well, you just have a matter multiplied by a constant speed. What could that possibly be? It doesn't change because the speed of light doesn't change, and the matter itself doesn't change. Mass doesn't change. And what he discovered was that it actually does. That the mass actually has to change in order for this conservation of energy equation to be true. And it's not just that it changes, it actually can be converted. That matter can be changed, can actually be converted from one form of stuff to another kind of thing entirely, and that thing is energy. So that matter can actually be destroyed and turned into pure energy. And the reverse is also true, that energy can be destroyed and turned into pure matter. And both of those things have been observed. The first time they observed matter being turned into energy was when they created the first nuclear reactor under the football stadium at the University of Chicago. And they created a nuclear reaction where a little bit of uranium ore was destroyed and turned into a lot of energy, it turns out, because that C is a big number. So it just takes a tiny bit of M and you get a big amount of E out for the C squared. A big number squared is, of course, humongous. So it turns out that those things are not conserved. Matter can be turned into energy, energy can be turned into matter. And it also begs the question, are they just kind of the same thing? Maybe matter and energy are very much the same thing and just different forms of the same thing. We haven't really answered that question. There are a lot of people exploring it, but it's a question that's up in the air. So anyway, this thing here, this momentum, is conserved and has never been proven to not be conserved. People have tried and not been able to do it. Another interesting thing about momentum that is in the history, interesting in the history. Let's see, where's my picture? I don't have the picture out right now. It's probably on one of those boards over there. But if you go back into the history of science, this woman here is one of the first women to really get credit for being a great scientist and really changing science. But she certainly wasn't the first. There were many before her. This woman lived at least 100 years before her, Ada Lovelace. She essentially worked out all of the paradigms for computer programming long before computers ever existed. And we still use her work to program computers today. She was amazing. But during her time, she didn't necessarily get all the credit for her work she should have, because it was a man's world. It was this very sexist, very divided world where women were expected to go and do their doilies, and men were expected to be the amazing, people that they of course were, which was kind of ridiculous because there were so many contradictions to this that it was undeniable that this was a stupid way to think of life and think of humans. But it persisted for way too long. But anyway, the point is that one of these, one woman actually did get credit for her work for interesting reasons. I don't know if we've talked about her. Have we talked about Emily du Châtelet yet? Looks like not. I can't spell, obviously. Emily du Châtelet. She was the daughter of a very wealthy aristocrat in France, and the sister of two brothers. Her father and brother were scientists and mathematicians, natural philosophers as they called them at the time, and she was working right along with them. And they were fairly well enlightened. These brothers and father did not necessarily want to, one of the things that was often done during that time is that women would do some work in science or math, and then somebody close to them who was male would take credit for it. maliciously, and kind of shoved the woman into the shadows, and this man would get all this credit for the work. But her brothers and father actually wanted her work to be known, but they knew that if they published her work openly, that it would be scoffed. But they knew that her work was important. She was working on energy and momentum. She was trying to actually prove that there was a difference between the two, and that one of them, involved mass times velocity, the other one involved mass times velocity squared, and that they were very different beasts in the physics world. And they actually began publishing her work, making her work public in sly ways, using pseudonyms, not taking credit, but giving her a pseudonym, a male pseudonym. But eventually they were able to work her into the limelight. And with the help of the fact that being an aristocrat, she was thrown into many circles with many important people, and one of those people was Voltaire, who was a philosopher at the time and very forward-thinking. And he was going to have none of this, trying to, hide women in the shadows. And they eventually, purportedly became lovers, and eventually she had access to all kinds of famous people who would listen to her because Voltaire was on her shoulder or on her elbow or whatever. So it was just kind of interesting that to attract Voltaire's eye, you definitely had to be an interesting person, and so she definitely was. But she actually paved the way for Einstein to make his discovery, because without her discovery of what energy actually was, his discovery of what this was would have been at least delayed, if not completely turned over. So many great scientists of both sexes throughout the years, but not all of them got the recognition they deserved, unfortunately. And it's even true of men too, because if you weren't wealthy, of course, you didn't get any recognition either. And it wasn't until probably Faraday that the first non-wealthy, non-aristocratic scientist began to get recognition for his work. So this thing, these social problems we had to overcome were often first overcome in science, because they knew the science was important. All of society knew they needed the science. They needed Faraday to go to the next step in electricity. And if they didn't give him credit for his work, he was going to just stop working. They knew that. Or he was going to go somewhere where he could work freely, which was America. And the English did not want their scientists going to America, especially not in the 1700s, when America had just broken away from England. So there was a lot of interesting things going on in politics that actually drove the science and drove the social norms, the change in social norms. It's all very, very interesting. So anyway, we're done for today. Go ahead and work on the math. We will give you some time to work on the homework tomorrow, and answer questions. And we'll also cover some more, maybe one more section from the book tomorrow to move on. But anyway, have a good day. Man, that goes quickly. 50-minute class. Yes, I got it. Thank you.